Thinking about cables and how cables transmit data. Okay, now there's a physical principle, and I choose the word physical importantly, like it's physics, right? There's a physical principle at work in physical cables that allows them to transmit data, and here's the way it works. Okay. If we want to transmit data, we need some kind of medium. Okay, and so far we've talked about the fact that, for instance, as I'm speaking to you right now, I am transmitting vibrations through the air, and so the medium is all of this, oxygen and nitrogen that's flying around, which very conveniently vibrates helpfully so that you can hear what I'm saying, right? If we somehow lived in a universe where we didn't have gas everywhere, but everything was just solid objects, they don't vibrate so well when I'm trying to speak through my vocal cords. And in the same way, if we lived in a vacuum, if we were organisms that lived in vacuums, right? And by the way, you're like, organisms can't live in vacuums. That's not true. Some can, very exotic ones, but that's beside the point. If we lived in a vacuum, again, I couldn't transmit signals to you audibly, right? Because there's nothing to vibrate. So I would resort to, well, how would you communicate with someone in a vacuum? Okay, good. So you can see each other. So even though sound, which is vibrating air, doesn't work through a vacuum, light, photons can travel through a vacuum just fine. Okay? Now, what we've been talking about so far is electricity. So we need a medium for electrical signals to travel. Okay? And since very, very long time ago, we've known that metal is a good medium for electricity. Okay? It's a good medium for electricity. It transfers electricity very effectively. Okay? In fact, that's what makes it a metal. And so we actually give this a special name. We say that it's conductive, right? It conducts electricity. Okay, electricity can pass through it. I suppose in the same way, using the same language, right? We could say that air conducts vibrations. That sort of makes sense. That there's a signal we want to send. Okay, electricity. That's the signal. And we need a medium that can handle and hold that signal and send it along without any sort of interference or anything like that. Okay? So therefore, let's come back. This is the principle by which all cables transmit data. They're a medium that can transmit some kind of signal, usually electricity. Okay? But that creates a problem. Okay? And these two videos are talking about it. What's the problem when you send electricity through a wire, through any kind of metal, actually, through any conductor? What's the problem? Yes, sort of. What distance is a problem, but why is this a problem? It has to do with these two videos. What were they talking about? They were talking about the relationship between two different things. What were they? People who were here. Okay, the idea that there's electricity and there's magnetism, which seem like very different things to us, right? One of them just sticks things to a fridge, and the other one hurts if you touch it, right? But actually, we know that they're part of one force. That's why we call it the electromagnetic force, okay? So here's the problem. Number one, when you've got electricity going through this, it's generating, let me get a different color. It's generating a magnetic field, okay? So as it goes through, magnetic fields are being sort of given off, okay? So why would that be a problem? Well, number one, that means you're losing parts of the signal, okay? So that's kind of not good. But number two, if I wanted to send one signal along here, no problems, okay? But usually, we don't just want to send one signal, we want to send lots of signals. So here's another cable, right? Now what's going to happen is, if we're trying to send two different things along these two different cables, right? Both of them are giving off magnetic fields. And they're giving off different ones because they're sending different signals, okay? So you can see what's going to happen here. You guys get two magnets, and as you push them together, what happens? If, say, they were opposite, we're putting, not opposite, if they were the same poles, right, and you'd push them together, they would repel each other, right? In other words, these two magnetic fields are interacting, okay? Does that make sense? Now, that's kind of cool when you're playing around with magnets, right, or if you want to stick something to a fridge, but that's not so cool when you want to transmit signals. Why not? Remember the idea that there was electricity and a magnetic field, right? So far we've said that when you've got one, it produces the other. Yes? But in the same way, and you might have seen this in the very first video, right? If you've got this one, you're also producing this. So these both interfere with each other, okay? So what's happening back up here? One signal is getting sent along and it's giving off a magnetic field, okay? But that means it's interacting with this magnetic field, changing it, which also changes the signal, okay? That's a big problem. If you want to send things, you don't want them, going along and then getting changed by all kinds of things. And you don't even need another wire. It could be anything, anything which can have some kind of magnetic interference here is going to change your signal, all right? So, what was the principle? That electricity can travel along this medium because it's conductive. But the problem is, you've got this other force, magnetism, which complicates things. Okay, because if you want to send a signal, you just don't want any particular electricity. You want a specific flow of electricity, which is your signal. Okay.